So we're looking at our log function. Yesterday we saw how to differentiate it. Integrating it is a little bit more involved, and we actually have to use a technique that we'll see later in extension 2, how we'll deal with that. So at this stage it's not integrating logarithms, but it's really going back, doing the reverse of yesterday. So if we notice we have the situation where the derivative is on the function. Now if I've got that situation, then it must have come from the log of function x. So just going back the other way. So it's something to look out for when we're looking at integrals. So something like this. Previous to this idea, we would have said, oh look, I've got a fraction, I'm integrating, I've got to put this in the index form. So I'd go 7 minus 3x to the power of negative 1. And remember, when we integrate, we add 1 to the power over the power. But when you add 1 to negative 1, you get 0. Oh, that's okay for the new power, but in the fraction, when you go over the power, you're now putting 0 on the bottom of the fraction. As you know, we can't have 0 on the bottom of the fraction. So you see that sort of situation, you go, hang on, something else is happening here. I must be looking for something else. So can I create a situation where it's derivative on function? So when you're basically dealing with polynomials, you want the degree of the top to be 1 less than the degree on the bottom. Because when you differentiate a polynomial, you take 1 off the power. So I've got a linear function. I need a constant on the top, which I've got, which is good. But I want negative 3. I don't want 1. So that's easy enough to change. I can put negative 3 on the top, but to balance it out, I've got to divide by negative 3 as well. Derivative on function, so I now know that's going to log of 7 minus 3x. So I've got negative 1/3 lots of 7 minus 3x. I suppose you could, if you wanted to, bring the negative 1/3 in as a power. Doesn't really matter. Again, I guess it just depends what you're going to do with that answer. Plus, of course, a constant. So same idea, linear function on the bottom. I'd like a constant on top. The constant I'd like is 8, because that's the derivative of 8x. So let's make it 8, but to balance it out, I've got to divide it by 8. So I get an 1/8 of the log of 8x plus 5. Again, we're okay, because the order of the bottom is 6 of that polynomial. The top is 5, it's 1 less. So I should be able to create the derivative on top. And the derivative of x to the power of 6 is 6x to the power of 5. So I multiply the top by 6, divide by 6 to balance it out. I've got derivative on function, so a 6 log x to the 6 minus 2, plus of course a constant. Now this is interesting. 1 on 5x. Alright. Well, I'd like derivative on function. So I'd like 5 on 5x. So multiply the top by 5, divide by 5. I have derivative on function, and I get 1/5 the log of 5x plus a constant. Fair enough. But what about if I thought about this a different way? Because remember, with integration we can factorise out. It's a grouping symbol. But I can only factorise out constant numbers. I can't factorise out the pronumerals. So I could bring the 1/5 out the front. And now my integral is 1 on x, derivative on function. So the answer is 1/5 the log of x plus a constant. We got 2 different answers. Or do we? Why are they the same?
You can change log 5x to log 5 plus.
Yeah. So even though I've written plus c for plus a constant, they would actually end up being different constants. Because you could use your log law in the first one and change that to 1/5 log 5 plus 1/5 log x, and a 1/5 log 5 is a constant. So they are the same answer, which does make it very interesting when you're doing these problems. Because you might look at the answer in the back and think you're wrong, but you might actually be right. They just might have done it a different way, and you actually got an equivalent expression. It also makes fun for myself when I have to mark your papers and that, because I'm expecting a certain answer. You might come up with something else, and I've got to go, oh, hang on a sec, is that the same thing? And so we have to work that one out. So just be a little bit careful, of course, when you're checking your answers on these ones. Well, this is no good. I've got a linear function on a linear function. I want it to be 1 less. So when you get this situation, if if you see the order of the numerator is greater than or equal to, before you do any integrating, do a polynomial division. So this one, well, if we needed to, there's my division. So I could rewrite this as 2 minus 1 on 2x plus 1. And now I've got two things I can integrate, because the 2 would just go to 2x. And then with the fraction, I just need to create derivative on function. So I'd end up with 2x minus a half of log 2x plus 1, because I needed 2 on the top, but to balance it out, I need to divide by the 2 as well. Let's do a definite integral. And to make life easy, I've already got the derivative on the function here. So we can go straight to the log of x squared plus 1. Now, this middle line that I put in, you might not need. Because you're always going to get the situation where you go log minus log. You're just substituting different numbers in. And your log laws say, well, subtraction is a fraction. So I know whatever I get when I substitute the top number in will go to the top of the fraction and the bottom. So you could legitimately just go from log x squared plus 1 straight to 5 on 2 and miss that middle line, if you realise that. So there it's log 5 on 2. The old differentiate and hence integrate. Basically, they're giving us a big hint. Differentiate x cubed log x. Okay. If I differentiate x cubed log x, write down the first, diff the second, plus write down the second, diff the first, tidy it up, there it is. So what do I know? I know that when I differentiate x cubed log x, I get x squared plus 3x squared log x. Therefore, when I integrate x squared plus 3x squared log x dx, I get x cubed log x. But that's when I now look at this, and instead of just being simply a statement, I'm looking at it and thinking of it like an equation, where I can move terms from one side to the other. And what do I want to make the subject? The integral of x squared log x is what I want to make the subject. So we have a rule with integration, remember, is we can separate them up into individual pieces in the addition. So I can change this x squared plus 3x squared log x to be the integral of x squared plus 3 times the integral of x squared log x, and then I've moved the integral of x squared over to the other side. And so now I've got a statement which says, well, 3 times the integral I'm looking for is x cubed log x minus whatever the integral of x squared is. Integrate x squared and I get 1/3 x cubed, but that's what 3 lots of it is. So divide everything by 3, I'll get 1/3 x cubed log x minus 1/9 x cubed. Notice I didn't bother going and 1/3 of a constant. I mean, a constant is just a constant. Yes, it's the same pronumeral, but we're just saying there's some constant number there. There we go, a little quick one for today.